In this lecture, we'll find out the length of line segment X. In the drawing, we have two quarter circles. Those two quarter circles touch each other at this point, point B. In addition, we know that line segment AB equals to 1 unit in its length, and line segment QS equals to line segment SP. And our mission is to find out the length of this line segment BC is equal to X. So first of all, because of the fact that this is a quarter circle, it means that PA and AB, they are both the radii of this quarter circle, therefore they are equal to each other. But AB equals to 1, therefore PA must be also equal to 1. Likewise, this is a quarter circle, and therefore QC and BC, they are both the radii of this quarter circle, therefore they are equal to each other. That is to say, BC equals to QC. But BC equals to X, according to what's given as the question, therefore QC must be also equal to X. X is the line segment that we are looking for. We have to find out the length of line segment BC that is equal to X. In the next step, we'll join points P and B by a straight line, and we'll also join points Q and B by a straight line. By joining points P and B, we created the right triangle, triangle PAB. In both those two quarter circles, this angle equals to 90 degrees and this angle equals to 90 degrees. It is true in any quarter circle. So we have here the right triangle PAB. So I copy the right triangle PAB in a new page and we'll implement the Pythagoras theorem in this right triangle, triangle PAB. Here by PT is abbreviation for Pythagoras theorem. So actually, this is the right triangle, triangle PAB that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle, triangle PAB, PB square equals to PA square plus AB square. PB square, that is the square of the hypotenuse, must be equal to PA square plus AB square. So PB square equals to PA square. PA is 1, therefore PA square is 1 square, that is 1. Plus PB plus AB square. AB is 1, therefore AB square is 1 square, that is also 1. So in total PB square equals to 1 plus 1, that is 2. So PB square equals to 2. Here we take a root out of this equation. And finally we get that PB, the hypotenuse PB equals to the square root of 2 units in its length. So we can write down here in the original drawing that the hypotenuse PB equals to the square root of 2 units in its length. Likewise, I'll copy before that we have in the right triangle PAB, PA equals to AB. And we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides we have those two angles that must be also equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because of the fact that those two angles are equal to each other. And we also know that the sum of the angles in the right triangle PAB must be equal to 180 degrees according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have inside the right triangle PAB? You have this angle alpha, this angle is also alpha. Alpha plus alpha is 2 alpha, plus this angle that is 90 degrees. In total, the sum of those three angles must be equal to 180 degrees, according to the rule that I mentioned. So we found out that 2 alpha plus 90 degrees equals to 180 degrees. Here we subtract 90 degrees from this equation, and we get that 2 alpha equals to 180 degrees minus 90 degrees, it is 90 degrees, so 2 alpha equals to 90 degrees. We divide this equation by 2, and finally we get that alpha equals to 90 degrees over 2, that is 45 degrees. So actually, this is angle alpha, that is equals to 45 degrees in its size. And this is also angle alpha that is equal to 45 degrees. So in the next step we will focus on the right triangle, triangle QCB. In this right triangle, triangle QCB, side QC equals to side CB. So if we repeat on the same process that we did in this right triangle PAB, in the right triangle QCB, we arrive to the conclusion that those two angles, each of them is equal to 45 degrees. So this angle equals to 45 degrees, and this angle equals to 45 degrees. It is very easy to see it because, again, those two sides are equal to each other, and we have the rule that in front of equal sides in the triangle are equal angles, so those two angles must be also equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha. And then we know that the sum of the angles in the right triangle QCB is equal to 180 degrees. That is to say, alpha plus alpha, that is 2 alpha, plus 90 degrees equals to 180 degrees. We subtract 90 degrees from the equation, and we get that 2 alpha equals to 90 degrees. We divide the equation by 2, and finally we get that alpha equals to 45 degrees. So those two angles, each of them is equal to 45 degrees in size. In the next step, I will copy this right triangle to the right triangle QCB, and we will implement the Pythagoras theorem in this right triangle, triangle QCB. Here by PT is the abbreviation for Pythagoras theorem. actually, this is the right triangle QCB that I covered from the original drawing. In this right triangle QCB, according to the Pythagoras theorem, QB squared equals to QC squared plus BC squared. So QB squared, that is the square of the hypotenuse, equals to QC squared. QC is x, therefore QC squared is x squared plus BC squared. BC is x, therefore BC squared is x squared. So in total, QB squared equals to x squared plus x squared, that is 2x squared. So here, QB squared equals to 2x squared. We take a root out of this equation, and finally we get that QB equals to the square root of 2x squared. That is to say, QB equals to the square root of 2, and the square root of x squared is x. So in total, again, QB equals to the square root of 2 and times the square root of x squared, the square root of x squared is x. So in total, QB, that is the hypotenuse here, equals to the square root of 2 times x units in its length. So I'll write it down in the original drawing that this QB, the hypotenuse QB, equals to the square root of 2 times x units in its length. Okay. In the next step, I will present to you rule number 3, and we will implement rule number 3 in our drawing. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So in the drawing we have the straight line AB. So if we focus on the upper side of this straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to this rule, rule number 3. So which angles we have at the upper side of AB at point Q? We have this angle alpha and the other angle beta. So in total, alpha plus beta must be equal to 180 degrees. You can actually implement rule number 3 in our drawing. Why? Because in our drawing we have the straight line AC. So if we focus on the upper side of the straight line AC at point B, here the sum of the angles must be equal to 180 degrees according to rule number 3. So which angles we have at the upper side of the straight line AB at point B? We have, but before that I will copy the straight line AC in a new page and also point B, and we'll implement rule number 3 in the new drawing. So actually, this is the straight line AC that I copied from the original drawing. This is point B. So we will implement on this straight line AC the rule number 3. So if you focus on the upper side of this straight line AC at point B, here the sum of the angles must be equal to 180 degrees according to rule number 3. So which angles we have at the upper side of AC at point B? We have this angle that is equal to 45 degrees, plus the missing angle, we define the missing angle as x, plus this missing angle that is also this angle that is equal to 45 degrees. In total, the sum of those three angles must be equal to 180 degrees according to rule number 3. So here we have 45 degrees plus 45 degrees is 90 degrees. So 90 degrees plus x equals to 180 degrees. Here we will subtract 90 degrees from this equation. And finally we get that x equals to 180 degrees minus 90 degrees, it is 90 degrees. So I actually found out that the missing angle here, x equals to 90 degrees in its size. So you can write here, this is the missing angle, x. Angle PBC is angle x, angle PBQ is x, and x equals to 90 degrees in its size, that is to say it is a right angle. And because of the fact that angle PBQ is a right angle, it means the triangle PBQ is a right triangle. So I'll copy the right triangle PBQ in a new page, and we will block this right triangle PBQ. We have a rule that any triangle can be blocked by a circle, and especially the right triangle PBQ. Okay. So actually, this is the right triangle QBP that I copied from the original drawing. And I blocked this right triangle QBP by this circle. So in the drawing we have peripheral angle PBQ. This is peripheral angle PBQ that equals to 90 degrees in its size. So I write it down. Peripheral angle PBQ equals to 90 degrees in its size. And we have rule number 5 that relates to any peripheral angle that is equals to 90 degrees. According to rule number 5, any peripheral angle that is equals to 90 degrees must rest on the diameter of the circle. Okay, so in the drawing we have peripheral angle MAN that is equal to 90 degrees in size. According to this rule number 5, because of the fact that peripheral angle MAN equals to 90 degrees, this peripheral angle MAN must rest on the diameter of the circle. From the drawing itself, it is very easy to see that this peripheral angle MAN rests on chord MN. And indeed, chord MN is the diameter of the circle. Why? Because of the fact that chord MN passes through point O, that is the center of the circle. Therefore, Mn for the Mn is the diameter of the circle. So in conclusion, we can say that because of the fact that peripheral angle MAN equals to 90 degrees, it rests on the diameter of the circle. Or any peripheral angle that is equal to 90 degrees rests on the diameter of the circle. So we can implement rule number 5 in our drawing. Why? Because in our drawing, we have this peripheral angle QBP that is equal to 90 degrees, and therefore, according to rule number 5, this peripheral angle QBP rests on the diameter of the circle. From the drawing itself, it is very easy to see that peripheral angle QBP rests on chord QP, therefore chord QP, according to rule number 5, is the diameter of the circle. So if we define the radius of this circle as x, then the diameter QP must be equal to 2x from one side, but from the other side it is given as the question that side QS equals to side SP. So if we define side QS as x, then side PS must be also equal to x because they are equal to each other. So the length of QP or PQ, it is the same, equals to PS plus SQ. PQ equals to PS plus SQ, that is to say, PQ in total equals to PS, that is x, plus SQ, that is also x. So in total, PQ equals to x plus x, that is 2x. Or PQ or QP, it is the same. So from the other side, we actually found out that here if we define the radius of this circle as r, then the diameter of this circle QP must be equal to 2r from one side. But from the other side, the other side now found out that QP equals to 2x. QP equals to 2x. And from those two equations, QP equals to 2r and QP equals to 2x, we will derive that 2r equals to 2x. R equals to 2x. Here we'll divide this equation by 2, and finally we get that r equals to x. So the radius of this circle r equals to x. According to our definition, PS equals to x and x equals to r, and also here SQ equals to x and SQ equals to x, and we just right now found out that x equals to r. So in the next step, I'll copy this point S to our new drawing here. Repeat again, and copy point S from the original drawing to the new drawing here. And we just right now found out that QS equals to R and PS also equals to R. Again, PS equals to R and QS also equals to R. That is to say, at point S, those two radii touch each other. Again, those two radii touch each other at this point S. Therefore, point S is the center of the circle. So I write it down. Point S is the center of the circle. In the next step, I will join points S and B together by a straight line. Point S is the center of the circle, point B is the point of the circle itself, therefore SB is the radius of this circle that is equal to R. Actually, we found out that those three line segments PS, SQ, and SB are all the radii of this circle, therefore they are equal to each other. So here we join points S and B together by a straight line. And we just like that found out that SB is also the radius of the previous circle, that is to say it is equal to R. And therefore, again here, SB equals to SQ equals to SB. Okay, so in the next step, we'll do a construction, that is to say, we will complete this quarter circle to a circle. I repeat again, we complete this quarter circle to a circle. So I'll copy this quarter circle in a new page and then we will complete it to a circle. Okay. So actually, this is the quarter circle that the comet of the original drawing. We'll join points Q and B together by a straight line. We have already found out that SQ equals to SB. They are both the radii of the previous circle, therefore they are equal to each other. Okay, so now I will complete this quarter circle that I call it from the original drawing to a circle. So I completed the quarter circle to a circle. In the next step, I will present to you a new rule and we will implement the new rule in our drawing. The new rule is rule number 13. According to rule number 13, a central angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have this circle. Inside this circle we have peripheral angle ACB. This is peripheral angle ACB that is equal to theta in its size. And peripheral angle ACB is subtended on arc AB. Again, this peripheral angle ACB that is equal to theta in its size is subtended on this arc AB. In addition, we have another angle This is the central angle AOB. The central angle AOB is also subtended on the same arc AB. So we have the peripheral angle is subtended on the same arc as this central angle. And therefore, according to this rule number 13, the central angle must be twice as large as the of this peripheral angle that is subtended on the same arc AB. And because of the fact that this peripheral angle equals to theta, then the central angle must be equal to 2 theta. It is twice as large as this peripheral angle ACB. So we can actually implement rule number 13 in our drawing. Why? Because in our drawing we have peripheral angle QSB. This angle is the peripheral angle QSB. This peripheral angle QSB is subtended on arc QB. Again, this peripheral angle QSB is subtended on this arc QB. And in addition, we have here the central angle QCB. This is the central angle QCB, and this central angle QCB is also subtended on the same arc QB. So here we have a peripheral angle that is subtended on the same arc as this central angle. Therefore, this peripheral angle must be twice as large as this peripheral angle that is subtended on the same arc QB. So first of all, we must find out the size of the central angle QCB, and the peripheral angle must be equal to half of the central angle. So what is the size of this angle, the central angle QCB? In order to find out the size of this central angle QCB, I present to you a new rule, and we'll implement the new rule in our drawing. The new rule is rule number 6. According to rule number 6, the sum of the angles around the point will always add up to 360 degrees. So in the drawing we have this point A. According to this rule number 6, the sum of the angles around this point A equals in total to 360 degrees. In order to prove that rule number 6 is true, I did here, I drew the straight line, this straight line that is passes for point A. Again, the straight line here passes for point A. So here we can implement rule number 3. According to rule number 3, the sum of the angles on the upper side of this straight line at point A equals to 180 degrees from one side. From the other side, the sum of the angles in the lower side of this straight line at point A must be also equal to 180 degrees. So in total, the sum of the angles in the upper side plus the sum of the angles in the lower side of this straight line at point A equals to 180 degrees plus 180 degrees, that is 360 degrees, exactly according to this rule, rule number 6, that says that the sum of the angles around point A equals to 360 degrees. So we can actually implement rule number 6 in our drawing. Why? Because in our drawing, if you focus at point C here, you know that the sum of the angles around point C in total must be equal to 360 degrees. So which angles we have around point C, we have this angle that is a right angle, it is equal to 90 degrees, plus this missing angle. In total, the sum of those two angles must be equal to 360 degrees in the sinus. So, the missing angle here must be equal to 270 degrees. Why? Because 270 degrees plus 90 degrees, it is 360 degrees, exactly according to rule number 6, that says that the sum of the angles around point C must be equal to 360 degrees. So, the missing angle is angle QCB, that is actually the central angle QCB. So in conclusion, found out that the central angle QCB equals to 270 degrees according to rule number 6, and therefore the peripheral angle QSB that is subtended on the same arc QB must be equal to 270 degrees over 2, that is 135 degrees. So we will focus on the triangle BSQ. This triangle BSQ is an isosceles triangle. Why? Because side BS equals to side SQ. We already found out that both BS and SQ are the radii of the previous circle, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha because of the fact that those two angles are equal to each other. And we also know that the sum of the angles in any triangle is equal to 180 degrees, and especially it is true in the isosceles triangle, triangle QSB. Okay, so here the sum of the angles in the isosceles triangle, triangle QSB must be equal to 180 degrees. So which angles we have inside the isosceles triangle, triangle QSB? We have this angle alpha plus this angle that is also alpha plus 135 degrees must be equal to 180 degrees. So alpha plus alpha is 2 alpha, so 2 alpha plus 135 degrees. In total, the sum of those three angles must be equal to 180 degrees according to the rule that I mentioned. So here we subtract 135 degrees from this equation, and you'll get that 2 alpha equals to 180 degrees minus 135 degrees is 45 degrees. So 2 alpha equals to 45 degrees. Here we will divide this equation by 2, and finally we will get that alpha equals to 45 degrees, alpha equals to 45 over 2 degrees. So this is angle alpha, this is equal to 45 over 2 degrees, and this is also angle alpha that is equal to 45 over 2 degrees. Okay, so in the next step I will copy the right triangle PBQ in a new page, and we will analyze this right triangle PBQ. Here we have already found out that this is angle alpha that is equals to 45 over 2 degrees in its size. Okay, here angle alpha equals to 45 over 2 degrees. So I'll copy the right triangle PBQ in a new page. Again, this is angle alpha. This is equals to 45 over 2 degrees. Side PB of the rectangle PBQ equals to the square root of 2 units in its length. Side QB equals to the square root of 2 times x units in its length. Repeat again. This is the rectangle PBQ that I go between the original drawing. In this rectangle PBQ, tangents 45 over 2 degrees equals to PB over BQ. Again, tangents 45 over 2 degrees equals to PB over BQ. So I write it down. Tangents 45 over 2 degrees equals to PB over BQ. PB is square root of 2 and BQ is square root of 2 times x. So here we have square root of 2 in the numerator and we have square root of 2 in the denominator, so square root of 2 will get cancelled. And this expression, after we cancel square root of 2, is equals to 1 over x. So in conclusion, we found out that according to equation number 1, tangents 45 degrees, tangents 45 over 2 degrees equals to 1 over x. So write it down here. According to equation number 1, tangents 45 over 2 degrees is equals to 1 over x. This is according to equation number 1. But we also have the trigonometric identity that states that tangents 2 theta equals to 2 tangents theta over 1 minus tangents square theta. Okay. Again, tangents 2 theta equals to 2 times tangents theta over 1 minus tangents square theta. Now we'll define angle 45 over 2 degrees as theta. Theta equals to 45 over 2 degrees according to our definition. So if theta equals to 45 over 2 degrees, it means that 2 theta will be equal to 45 degrees. Okay. In the next step, we will substitute theta in this trigonometric identity by 45 over 2 degrees, and we will substitute 2 theta by 45 degrees. This will be equation number 2, and we'll get that tangents 2 theta, and 2 theta is 45 degrees, equals to 2 times tangents theta, and theta is 45 over 2 degrees over 1 minus tangents square theta, and theta is 45 over 2 degrees. In conclusion, we found out that according to equation number 2, tangents 45 degrees equals to 2 times tangents 45 over 2 degrees over 1 minus tangent square 45 over 2 degrees. Tangents 45 degrees is 1, so we substitute tangents 45 degrees in this equation number 2 by 1. And it is equals to 2 times 45 over 2 degrees. Here we will define tangents 45 over 2 degrees as t, and we'll substitute tangents 45 over 2 degrees in this equation number 2 by t. So 2 times tangents 45 degrees over 2 is 2t over 1 minus tangents square 45 over 2 degrees. So if tangents 45 over 2 degrees equals to t, then tangent square 45 over 2 degrees will be equal to t squared. So we substitute tangent square 45 over 2 degrees by t squared. In conclusion, we found out that according to this equation number 2, one equals to 2t over 1 minus t squared. Here we multiply this equation number 2 by 1 minus t squared, and you will get that according to this equation number 2, 1 minus t squared equals to 2t. Here we will add to this equation number 2t squared, and we get that according to this equation number 2, 1 equals to 2t plus t squared. Here we subtract from this equation number 2, 1, and we get that according to this equation number 2, t squared plus 2t minus 1 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we'll find out the value of x according to the following formula, that x equals to minus b plus minus the square root of b squared minus 4 times a times c over 2a. Repeat again that this is a general formula for quadratic equation, and the solution to this quadratic equation is this expression: x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, t squared plus t squared plus 2t minus 1 equals to 0, the variable that we are looking for is t. So x equals to t. The coefficient a equals to 1, the coefficient b equals to 2, and finally the coefficient c equals to minus 1. And x equals to t. So the only thing that is left to do is to put the data inside the formula for x, and we find out the value or the values of t, because x equals to t. So here we substitute x by t. So t equals to minus b. B is 2, so minus b is minus 2, plus minus square root of b squared. B is 2, so b squared is 2 squared, that is 4. Minus 4 times a is 1, times c is minus 1. All divided by 2 times a is 1, so it is 2 times 1. So in conclusion, we found out that t equals to minus 2 plus minus. Inside the root we have 4, and minus 4 times minus 1 is plus 4. So in total, inside the root we have 4 plus 4, that is 8. Divided by 2 times 1, that is 2. In conclusion, we found out that t equals to minus 2 plus minus square root of 8 over 2. So t equals to minus 2 plus minus the square root of 8. 8 is 4 times 2, so we'll substitute 8 by 4 times 2 divided by 2. So here t equals to minus 2 plus minus the square root of 4 is 2. So inside the root we left only with 2 divided by 2. So in conclusion, we found out that t equals to minus 2 plus minus 2 times root of 2 over 2. So t equals to minus 2 over 2 is minus 1 plus minus 2 over 2 is 1. So in total, this expression equals to the square root of 2. In conclusion, we found out that t equals to minus 1 plus minus square root of 2. Or we can write down that t equals to the square root of 2 plus minus this minus 1. Because a plus b equals to b plus a. You can change the order. So here we will have two solutions that are possible for t. The first solution for t, that is the solution of the quadratic equation. The first solution for t is that t equals to the square root of 2 minus 1 it is actually, we have here the first solution for t is that t equals to the square root of minus 2 minus the square root of 1. This is the first solution. And the second solution for t is that t equals to the square root of 2 plus 1. So according to the second solution is that t equals to the square root of 2 minus 1. Again, the second solution is that t equals to the square root of 2 minus 1. And the first solution is that t equals to the square root of 2 minus 1. So according to the first solution, t equals to the square root of 2 minus 1. The square root of 2 minus 1 is a negative number. So according to the first solution, t is a negative number. But according to our definition, t equals to tangents 45 over 2 degrees. That is a positive number. So from the other side, P is a positive number. T is a positive number. A negative number can never be equal to a positive number, so we got to a contradiction here. And therefore we cancel this solution, and so only the second solution is left for T, that T equals to the square root of 2 minus 1. Again, according to our definition, T equals to tangents 45 over 2 degrees. So tangents 45 over 2 degrees equals to T, and T is square root of T, square root of 2 minus 1. T is square root of 2 minus 1. So here we have equation number 2 that says that tangents 45 over 2 equals to the square root of 2 minus 1. This is according to equation number 2. While according to equation number 1, we have already found out that this is equation number 1. According to equation number 1, we have already found out that tangents 45 over 2 degrees equals to 1 over x. So I write it down. According to equation number 1, we have already found out that tangents 45 over 2 degrees equals to 1 over x. So we have two equations for the value of tangents 45 over 2 degrees. Therefore, we'll create the equation number 3 that states that tangents 45 over 2 degrees according to equation number 1 must be equal to tangents 45 over 2 degrees according to equation number 2. Repeat again on equation number 3. According to equation number 3, tangents 45 over 2 degrees according to equation number 1 must be equal to tangents 45 over 2 degrees according to equation number 2. So tangents 45 over 2 degrees according to equation number 1 is 1 over x, and it must be equal to tangents 45 over 2 degrees according to equation number 2, that is actually square root of 2 minus 1. In conclusion, we found out that according to equation number 3, 1 over x equals to the square root of 2 minus 1. Here we'll multiply this equation number 3 by x, and we'll get that according to equation number 3, 1 equals to x times square root of 2 minus 1. So here we divide this equation number 3, by square root of 2 minus 1, and we get that according to this equation number 3, x equals to 1 over square root of 2 minus 1. And again, we actually found out that x equals to 1 over square root of 2 minus 1. So x equals to 1 over square root of 2 minus 1. Here we will multiply this side of the equation by square root of 2 minus 1, and that's by square root of 2 plus 1, and then we will divide it by square root of 2 plus 1. Okay? Square root of 2 plus 1 over square root of 2 plus 1 is 1. That is to say, we multiply this side of the equation by 1, so we change nothing. Therefore, this operation is allowable. And we get here that x equals, in the numerator we have square root of 2 plus 1 over, in the denominator we have square root of 2 minus 1 times square root of 2 plus 1. This expression equals to, according to the algebraic identity, that a minus b times a plus b equals to a squared minus b squared, according to this algebraic identity. Square root of 2 minus 1 times square root of 2 plus 1 will be equal to the square root of 2 squared, that is 2, minus 1 squared, that is 1. So in total, this expression equals to 2 minus 1, that is 1. In conclusion, x equals to the square root of 2 plus 1 over 1. It's actually square root of 2 plus 1. So x equals to either square root of 2 plus 1 units in its length, or in terms of numbers, x equals to 2.414 units. Repeat again. The length of this line segment BC, is equal to x, is equal to either square root of 2 plus 1 units, or in terms of numbers, BC that is equal to x is equal to 2.414 units. It is a little bit less than 2.5 units. Okay, in the next step, I'll summarize the lecture. In this lecture, we found out the length of this line segment BC is equal to x. In the drawing, we have two quarter circles. Those two quarter circles touch each other at this point B. In addition, we know that the length of line segment AB is 1 unit, and we also know that line segment QS equals to line segment SP. Again, our mission is to find out the length of this line segment BC that is equal to x. So here, this is a quarter circle. PAB is a quarter circle. In any quarter circle, this angle must be equal to 90 degrees. And AB, line segment AB and line segment PA, they are both the radii of this quarter circle, therefore they are equal to each other. And it is given as the question that AB equals to 1, therefore PA must be also equal to 1. Okay. So here, PA also equals to 1. Then, so, if we focus on the big quarter circle, QC must be equal to CB. They are both the radii of this quarter circle, therefore they are equal to each other. But BC equals to x, according to what is given in the question, that therefore QC must be also equal to x. Then we join points P and B together by a straight line, and we join points Q and B together by a straight line. Then I copied the right triangle PAB in the new page, and we implemented on this right triangle PAB the Pythagoras theorem. This is the right triangle PAB that I copied from the original drawing. PA equals to AB equals to 1. In this right triangle PAB, according to the Pythagoras theorem, PB squared equals to PA squared plus AB squared. So PB squared, that is the square of the hypotenuse, equals to PA squared. PA is 1, therefore PA squared is 1 squared, that is 1, plus AB squared. AB is 1, therefore AB squared is 1 squared, that is 1. So in total, PB squared equals to 1 plus 1, that is 2. PB squared equals to 2, we took out of this equation, and finally we found out that PB equals to the square root of 2 units. That is to say, the hypotenuse PB of the triangle PAB equals to the square root of 2 units in its length. Then we found out that PA equals to AB in this right triangle PAB. PA equals to AB equals to 1. And we have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we have those two angles that also must be equal to each other. Okay, so if this angle is alpha, then this angle must be also equal to alpha because of the fact that those two angles are equal to each other. You can apply the same thing on the right triangle QCB. Side QC equals to side BC. So in front of those two equal sides, we have those two angles that must be equal to each other. So if one angle is alpha, then the other angle must be also equal to alpha. So here we return to this triangle PAB. In this triangle PAB, the sum of the angles must be equal to 180 degrees. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. So which angles we have inside the right triangle PAB? We have this angle alpha, plus the other angle that is also alpha, plus this angle that is the right angle. In total they must be equal to 180 degrees. The same thing is true in the right triangle QCB. This angle is alpha, this angle is alpha, and this angle is 90 degrees. So the sum of the angles in the right angle QCB must be also equal to 180 degrees. So in both triangles, we actually can write down that alpha plus alpha is 2 alpha plus 90 degrees equals to 180 degrees. We subtracted 90 degrees from the equation, and finally we found out that 2 alpha equals to 180 degrees minus 90 degrees, that is 90 degrees. 2 alpha equals to 90 degrees, we divided the equation by 2 and finally found out that alpha equals to 45 degrees. So this is angle alpha that is equal to 45 degrees, and this is also angle alpha that is equal to 45 degrees. And here also, this is angle alpha that is equal to 45 degrees, and this is also angle alpha that is equal to 45 degrees. Okay, then I presented to you rule number 3, and we implemented rule. But before that, I copied the right triangle QCB in a new page, and we implemented the Pythagoras theorem in this right triangle QCB. This is the right triangle QCB that I copied from the original drawing. In this right triangle QCB, according to the Pythagoras theorem, QB square equals to QC square plus BC square. Again, QB square equals to QC square plus BC square. QB square, that is the square of the hypotenuse, equals to QC square. QC is x, therefore QC square is x square. Plus BC square. BC is x, therefore BC square is x square. So in total, QB square equals to x square plus x square, that is 2x square. QB square equals to 2x square. Here we took out of this equation and finally found out that QB equals to the square root of 2x square. That is to say, QB equals to the square root of 2, and the square root of x square is x. So in total, QB equals to the square root of 2 times x. So I can write down here in the original drawing that the hypotenuse QB of the rectangle QCB equals to the square root of 2 times x units. Then I presented to you rule number 3, and we implemented rule number 3 in our drawing. According to rule number 3, the sum of the angles on one side of a straight line is equal to 180 degrees. So, in the drawing we have the straight line AB. If you focus on the upper side of the straight line AB at point Q, here the sum of the angles must be equal to 180 degrees according to this rule number 3. So which angles we have at the upper side of AB at point Q? We have this angle alpha and this angle beta, so in total alpha plus beta must be equal to 180 degrees according to this rule number 3. Actually, you can implement rule number 3 in our drawing. Why? Because in our drawing, if you focus on the upper side of the straight line AC at point B, here the sum of the angles must be equal to 180 degrees according to rule number 3. So I copied the straight line AC with point B and with its angles in a new page, and we implemented rule number 3 on the straight line AC. This is the straight line AC that I copied from the original drawing. This is point B. So which angles we have at the upper side of the straight line AC at point B? We have this angle that is equal to 45 degrees plus the missing angle that we defined as x plus this angle that is equal to 45 degrees. In total, the sum of those three angles must be equal to 180 degrees according to rule number 3. So 45 degrees plus 45 degrees is 90 degrees. So in total, this side of the equation we have 90 degrees plus x that is equal to 180 degrees. Here we subtract the 90 degrees from this equation and finally found out that x equals to 180 degrees minus 90 degrees is 90 degrees. So x, this missing angle x equals to 90 degrees, it is a right angle. That is to say, angle PBQ, that is x, equals to 90 degrees in size. And therefore triangle PBQ is a right triangle. In the next step, I copied the right triangle PBQ in a new page, and we block this right triangle PBQ by a circle. We have the rule that any triangle can be blocked by a circle. This is the right triangle PBQ that I copied from the original drawing. We block this right triangle PBQ by this circle. So in the drawing we have peripheral angle PBQ that is equal to 90 degrees. And we have rule number 5 that relates to any peripheral angle that is equal to 90 degrees. According to rule number 5, any peripheral angle is equal to 90 degrees must rest on the diameter of the circle. In the drawing we have a circle, inside the circle we have peripheral angle MAN that is equal to 90 degrees. Therefore, according to this rule number 5, peripheral angle MAN must rest on the diameter of the circle. That is to say, MN is the diameter of the circle. So we can actually implement rule number 5 in our drawing. Why? Because in our drawing we have peripheral angle PBQ that is equal to 90 degrees. Therefore, peripheral angle PBQ rests on the diameter of the circle. That is to say, PQ is the diameter, PQ or QP is the diameter of the circle. So if we define the radius of this circle as R, then the diameter QP must be equal to 2R from one side, but from the other side, it is given us in the question that QS equals to SP. So if we define QS as X, then SP must be also equal to X because of the fact that they are equal to each other. So in total, QP equals to QS plus SP. That is to say, QP equals to QS, that is X, plus SP, that is also X. So in total, QP equals to X plus X, that is 2X. So QP equals to 2X. So from one side QP equals to 2R, from the other side QP equals to 2X. From those two equations, we will derive that 2X equals to 2R. 2X equals to 2R, we divided this equation by 2 and finally found out that R equals to X. So here, R equals to X and R equals to X. Then I copied point S from this original drawing to our new drawing here. I copied point S here. We just right now found out that SP equals to R and SQ also equals to R. That is to say, at point S, the two radii touch each other. And therefore point S is the center of the circle. Here, point S is the center of the circle. Then we join points S and B together by a straight line. Point S is the center of the circle, point B is the point of the circle itself, therefore SB is the radius of the circle that is equal to R. In conclusion, found out that PS equals to SQ equals to SB. They are all the radii of the circle, therefore they are equal to each other. So we join points S and B together by a straight line. SB is the radius of the prior circle, SQ and SB, they are also the radii of the prior circle, therefore they are equal to each other. So those three line segments, SP and SB, SP and SP, SB and SQ, they are both the radii of the previous circle, therefore they are equal to each other. Then I copied this quarter circle to a new page and I completed this quarter circle to a circle. So this is the quarter circle, the code from the original drawing. Then I completed this quarter circle to a circle. Here we have QS equals to SB, both the radii of the previous circle, therefore they are equal to each other. Then I presented to you rule number 13 and we implemented rule number 13 in our drawing. According to rule number 13, a center angle is twice as large as the peripheral angle subtended on the same arc. So in the drawing we have this circle, inside this circle we have peripheral angle ACB. This peripheral angle ACB equals to theta in its size, and this peripheral angle ACB is subtended on arc AB. Likewise we have the center angle AOB that is subtended on the same arc AB. So according to this rule number 13, the center angle AOB that is subtended on the same arc AB as the peripheral angle ACB must be twice as large as this peripheral angle ACB. And because of the fact that this peripheral angle ACB is equal to theta, then the peripheral angle AOB that is subtended on the same arc AB must be equal to theta. So we can implement rule number 13 in our drawing. Why? Because in our drawing we have this peripheral angle BSQ. This peripheral angle BSQ is subtended on chord QB. And we have also the center angle BCQ. This is the center angle BCQ that is subtended on the same arc QB. Therefore, so actually this is the center angle QCB. This is subtended on the same arc QB as the peripheral angle QSB. So according to rule number 13, the size of the center angle must be twice as large of the size of the peripheral angle that is subtended on the same arc QB. So we have to find out the size of the center angle QCB. In order to find out the size of this center angle QCB, I presented to you rule number 6 and we implemented rule number 6 in our drawing. According to rule number 6, the sum of the angles around a point will always add up to 360 degrees. So in the drawing we have this point A. According to this rule number 6, the sum of the angles around point A must be equal to 360 degrees. In order to prove that this rule number 6 is true, I draw this straight line that passes through point A. Here we can implement rule number 3. According to rule number 3, the sum of the angles on the upper side of this straight line at point A must be equal to 180 degrees. Likewise, the sum of the angles in the lower side of this straight line at point A must be also equal to 180 degrees. So in total, the sum of the angles in the lower side and the upper side at point A must be equal to 180 degrees plus 180 degrees, that is 360 degrees. Okay? Now, we can implement rule number 6 in our drawing. Why? Because in our drawing, if we focus at point C, according to rule number 6, the sum of the angles around point C must be equal to 360 degrees. So which angles we have around point C? We have this angle that is a right angle plus the missing angle. In total, the sum of these three angles, the sum of those two angles must be equal to 360 degrees according to rule number 6. Therefore, this is the missing angle. This missing angle must be equal to 270 degrees. Why? Because 270 degrees plus 90 degrees is 360 degrees. That is the sum of the angles around any point, and especially around point C. So, angle QCB, the center angle QCB equals to 270 degrees. And therefore, according to rule number 13, the peripheral angle QSB that is subtended on the same arc RQB must be equal to half of it. That is to say, it must be equal to 270 degrees over 2, that is 135 degrees. So, in the associated triangle BSQ, this angle equals to 135 degrees, and we already found out that QS equals to SB. And we have the rule that in front of equal sides in the triangle there are equal angles. So those two angles that are located in front of those two equal sides must be also equal to each other. So if this angle is alpha, then the other angle must be also equal to alpha, according to the rule that I mentioned. And the sum of the angles in any triangle is 180 degrees, and especially in the associated triangle QSB. So which angles we have in the associated triangle QSB? We have alpha plus alpha, that is 2 alpha plus 135 degrees. In total, they must be equal to 180 degrees. 2 alpha plus 135 degrees equals to 180 degrees. We subtracted 135 degrees from this equation, and finally found out that 2 alpha equals to 180 degrees minus 135 degrees is 45 degrees. Then we divided this equation by 2, and finally found out that alpha equals to 45 over 2 degrees. This is again alpha that is equal to 45 over 2 degrees, and this is also again alpha that is equal to 45 over 2 degrees. Then I copied the right triangle PBQ in a new page, and analyze this right triangle PBQ. This is the right triangle PBQ that I copied from the original drawing. PB equals to the square root of 2, BQ equals to the square root of 2 times x. And this is angle alpha that is equal to 45 over 2 degrees. According to, we have here in this right triangle PBQ, tangent 45 over 2 degrees is PB over BQ. So tangent 45 degrees is PB, that is square root of 2, over BQ, that is 2 times square root of x. Again, BQ is square root of 2 times x, and PB is square root of 2. We have square root of 2 in the numerator, square root of 2 in the denominator, so square root of 2 will get cancelled, and we left only with 1 over x. So this, according to equation number 1, we actually found out that tangent 45 over 2 degrees equals to 1 over x. Again, tangent 45 over 2 degrees equals to 1 over x. But we also have the trigonometric identity that states that tangent 2 alpha equals to 2 tangents alpha over 1 minus tangent square theta. Again, tangent 2 theta equals to 2 tangents theta over 1 minus tangent square theta. Then we defined angle theta as 45 over 2 degrees. If theta is 45 over 2 degrees, it means that 2 theta is 45 degrees. Then we substitute theta by 45 in this trigonometric identity by 45 over 2 degrees, and we substitute 2 theta by 45 degrees. And found out that according to this trigonometric identity, we have here tangents 2 theta. So it is tangents, and 2 theta is 45 degrees, according to our definition, equals to 2 times tangents theta. So it is 2 times tangents, and theta is 45 over 2 degrees according to our definition, all divided by 1 minus tangent square theta, and theta is 45 over 2 degrees according to our definition. So in conclusion, we found out that tangent 45 degrees equals to 2 times tangent 45 over 2 degrees over 1 minus tangent square 45 over 2 degrees. Then we defined tangent 45 over 2 degrees as t, and we substituted tangent 45 over degrees by t. And found out actually tangent 45 degrees is 1, and it is equals to 2 times tangent 45 over 2 degrees. And according to our definition, tangent 45 over 2 degrees is t. So in total, in the numerator we have 2t over 1 minus tangent 45 over 2 degrees. If tangent 45 over 2 degrees is t, then it means that tangent square 45 over 2 degrees is t squared. So in total, in the denominator we have 1 minus t squared. So in conclusion, found out that according to equation number 2, 1 equals to 2t over 1 minus t squared. We multiply this equation, equation number 2, by 1 minus t squared. And finally we found out that 1 minus t squared equals to 2t. We added to this equation, equation number 2, t squared, and found out that 1 equals to 2t plus t squared. Here we subtracted 1 from this equation, and finally found out that t squared plus 2t minus 1 equals to 0. Here, this equation is a quadratic equation, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula, that x equals to minus b plus minus 4 of b squared minus 4 times ac over 2a. In our specific quadratic equation, t squared plus 2t minus 1 equals to 0, the variable that we are looking for is t, so x equals to t, the coefficient a equals to 1, the coefficient b equals to 2, and the coefficient c equals to minus 1. Now, we'll put the data inside this formula, and we find out the value of the values of t, because x equals to t. So x equals to t, so we substitute x by t. And it is equals to minus b. B is 2, so minus b is minus 2, plus minus square root of b squared. B is 2, so b squared is 2 squared, that is 4, minus 4 times 8, that is 1, times 8, that is minus 1, over 2a. So it is over 2, and a is 1, so it is 2 times 1. So inside the root we have minus 4 times minus 1 is plus 4. So in total inside the root we have 4 plus 4, that is 8. In conclusion, found out that according to this equation, t equals to minus 2 plus minus square root of 8 over 2. So t equals to minus 2 plus minus 8 is 4 times 2 over 2. And the square root of 4 is 2. Inside the root we left only with 2. So in conclusion, found out that t equals to minus 2 plus minus 2 times square root of 2 over 2. So t equals to minus 2 over minus 2 is minus 1 plus minus square root of 2. Okay, so we can change the order here, and we get that t equals to square root of 2 plus minus 1. So t equals to minus square root of 2 minus 1. Because we have here two solutions that are possible for t. According to the first solution, t equals to minus square root of 2 minus 1. And according we can have here another solution for t, that t equals to square root of 2 minus 1. According to the first solution, t equals to the square root of 2 minus 1, that is a negative number. And according to our definition, t equals to times 45 over 2 degrees, that is a positive number. A negative number can never be equal to a positive number, so we got to a contradiction, therefore we cancel the solution, and we left only with the second solution that is possible for t, that t equals to the square root of 2 minus 1. And according to our definition, t equals to 45 over 2 degrees, so t is minus 45 over 2 degrees, and it is equals to the square root of 2 minus 1. This is according to equation number 2, while according to equation number 1, we have already found out that minus 45 over 2 degrees equals to 1 over x. So we have two different equations for minus 45 over 2 degrees. Therefore, we can do equation number 3 that states that minus 45 degrees, minus 45 over 2 degrees according to equation number 1 must be equal to minus 45 over 2 degrees according to equation number 2. Minus 45 over 2 degrees according to equation number 1 is 1 over x, and it must be equal to minus 45 over 2 degrees according to equation number 2, that is square root of 2 minus 1. So in conclusion found out that according to equation number 3, 1 over x equals to the square root of 2 minus 1. Here we multiply this equation number 3 by x, and found out that 1 equals to x times square root of 2 minus 1. Here we divided this equation number 3 by square root of 2 minus 1. And finally found out that x equals to 1 over square root of 2 minus 1. Again, x equals to 1 over square root of 2 minus 1. Then we multiply this side of the equation by square root of 2 plus 1, and then we divide it by square root of 2 plus 1. Actually, we multiply it by 1, therefore we change nothing. Therefore, this operation is allowable. So in conclusion, found out that x equals to, in the numerator we have square root of 2 plus 1, in the denominator we have square root of 2 minus 1 times square root of 2 plus 1. This expression is equals to, according to the algebraic identity, that a minus b times a plus b equals to a squared minus b squared. This expression will be equal to the square root of 2 squared, that is 2, minus 1 squared, that is 1. So in total, this expression equals to 2 minus 1, that is 1. In conclusion, found out that x equals to the square root of 2 plus 1 over 1 is the square root of 2 plus 1. So either x equals to the square root of 2 plus 1 units in itself, or in terms of numbers, x equals to 2.414 units. Repeat again, the length of this line segment BC that is equal to x, it is equal to either square root of 2 plus 1 units in its length, or BC that is equal to x equals to 2.414 units. Okay, thank you very much.